The final time complexity that we need to know about is what's known as logarithmic time complexity. And if you've never heard of a logarithm before, that's totally fine. But it plays a very important role in computer science and solving Leet Code questions and problems in general. So in this video, we're going to cover exactly what a logarithm is and what logarithm time complexity is in the context of these software engineering coding interviews. And a good way to get an intuition of what a logarithm is in computer science, let's just think of a real life scenario that might occur. So let's say we're playing a game and we want to pick a number from 1 and 100. The other person knows the number and we're trying to guess it in the least amount of guesses possible. And let's say they'll give you $100 if you can guess it in less than 10 goes. Now, would you take that bet? You probably would want to if you knew how to play the game properly. And it's pretty easy to play. Now, the worst way you could play the game, and it's more relatable to like a for loop or something like that in computer science, is you could start at 1 and guess 2, then guess 3, and do that all the way up to 100. But there's a much better way to play the game, and it may be intuitive, and that is, well, you guess the number 50, for example. Oh, and one of the key details is that the person has to tell you whether it's higher or lower. So let's say they're thinking of the number 72, for example, but we don't know that yet. Well, you say 50, they say, well, it's higher. You will say 75, so you've halved the numbers. You went from 100 to 50, and then, you say, well, it's a higher number. So you choose 75, and then they say it's lower, and then you cut out the number 75 to 100. So you effectively halved the remaining 50 numbers to 25. And then you do that a few times, and then eventually you arrive at your at the number that they chose in less than 10. So this is a very intuitive sort of conceptual understanding of what the effects of a logarithm do. So rather than looping through each number, which would be linear, which is pretty fast, but logarithmic in computer science usually involves dividing things into 2. So if you divide things into 2, you'll quickly realize, well, 100 numbers, you could work through that within 5, 6, 7, around 7 to 10 iterations. So that's, less than a tenth of the work that you need to do compared to the linear. And obviously, as the numbers get bigger and bigger, that scales even harder. So that's why the logarithm time complexity is really important in computer science and solving these problems, is because it's a faster way to do things if you're able to do it like that. So let's actually dive into some of the details of this. A logarithm is simply the inverse of an exponential. So let's consider 10 to the power of 2. So 10 squared, that's simply going to be equal to 100. But the question we're asking is, well, if you have the number 100, and you have a logarithm of base 10, what power is that going to give us? So let me just write that out, because that might have been a bit confusing. But basically a logarithm, so we actually just have the word here, logarithm. And logarithms are usually, well, if you've ever studied mathematics before, you'd know that base 10 is going to be the logarithm that is going to be the main base, which is different to computer science, but just to sort of spell that out there, because it's actually easy to learn this concept if you haven't studied logarithms extensively in mathematics, because the base sort of throws you off. Sort of like binary numbers, because we're so used to our 10 base system, we just sort of make some assumptions of what the numbers mean. So when you see the number 100 here, you think of the number 100. You don't think of the number, 4. So, 0 1s, 0 2s, 1 4 in binary. Similarly, what we do is we say, okay, well, if we want the inverse of 10 squared, so if we know we have the number 100, and then we sort of just take for granted that we have this base 10 here, what was the power that raised the base to be able to get that number? So it's basically this number here to the power of what gives us this number. So the very inverse of that. So basically, I just want to, I just want to have some formulas here. So basically, we've got, if 10 is our base, we'll let that be B, and then 2 is the power that we're trying to find. In this case, we already know what it is. So the base to the power of x is going to equal our y. So that's the formula for the exponential. Now the inverse, or the logarithm, is going to be, well, we take the logarithm, we just take the word log, and that sort of denotes the inverse of an exponential, to the b base here, and essentially, we plug in the value y, and that's going to determine our power x. So in our case here, log to the base of 10, with 100 as input, well, 10 squared equals 100. So that's the power that we've solved for, which is the inverse of the exponential. Okay, so that's great. So, why would we want to know that? A bit of information in computer science. Well, basically, the first thing to get out of the way is, this base 10 here, which, if you came across that before in mathematics, that's like the standard. But, in computer science, you got bits 0 or 1s, so intuitively it sort of makes sense to have a 2 there, but let's explain in a little more detail why. So basically what that means is this formula, though, since we know in computer science that it's going to have a base of 2, we can actually simplify b to equal 2. And because in computer science, it's just assumed that you're going to have a base of 2. It's such a common thing. So rather than saying log 2 every time, we just have LG. So if you see LG, that denotes base 2, particularly in the context of computer science, equals x. So let's explain this a little better, but specific to computer science. So, and I want to change the color here. So let's choose a white. So basically we know a few things. So just from our basic mathematical skills, we know that 2 to the power of 0 is going to equal 1. We know 2 to the power of 1 is going to equal 2. We know that 2 to the power of 2 is going to equal 4. And, if we continue on, let's do a couple more. 2 to the power of 7
That's going to equal 128. And then if we do one more, 2 to the power of 16, that's going to equal 65,500. Oops. 536. So hopefully I haven't lost anyone so far. But with our new knowledge that we have here of the logarithm, we know that this is essentially going to be equal to, or equivalent to saying, well, the log of base 2, which is this number here, of this number here, so 1, that's going to be equal to the power here, which is 0. So we're going to have log of 2 equal to 1. And often you'll see parentheses around these to denote that it's an input of a function. You have here log of 4 equals to 2. And then you have this log of 128 equals to 7. And finally here we've got log of 65,536 equal to 16. Okay, so all we've done is we've just sort of introduced this formula here for the inverse of a exponential with a base of 2. So, and just to sort of illustrate in this sort of format here, that's like saying 2 to the power of x equals y. And it might become clear why we choose 2. And that's because, you've got bits and it relates to binary. So if you've watched the previous videos on memory, we sort of talked about binary a little bit. And this makes more and more sense when we start doing things like binary search and graphs and stuff like that. But essentially, we want to know why this is useful, right? So we've just covered some basic mathematics here, but why do we care? Why does this matter? And why does it turn out to be so useful? So if you just notice this trend here though, notice that every time we double this input here, so we go from 1 to 2 to 4 and so on to 128, notice that this value here, it only increments up by 1. So essentially, if you think about that higher or lower number guessing game, when we played it correctly, basically you can see how it relates to halving the amount of the results each time. And we've already explained how that's more efficient than linear time. So, that this is sort of the intuition as to why this is so important. And this is sort of more of the conceptual understanding of the logarithm. We're actually going to see the logarithm in code in the binary search videos and other search/sorting videos. But basically, if you look at the graph of linear versus logarithmic time, so linear, it just completely depends on the number of inputs, right? So n, and this is O of n. So the time complexity completely relates to that. Whereas the logarithm time, it's more like this. And let me do that in a different color. it starts off a little worse, but we're considering what happens as it becomes infinitely large. It quickly sort of does this sort of thing here, because you can see that we've got such a large number here, but that's only 16 relative to, say, like 4 and 2. So 2 is really close to 16, but there's a big difference between 65,536 and 4. Whereas if you're looking at sort of linear time, well, if you look at the number 65,000, it's going to be related to 65,000, which is way, way worse, especially as things get bigger and bigger. So logarithmic time becomes better and better as n becomes large. And when we're dealing with time complexity, we are thinking about, well, what happens when n becomes large, unless otherwise specified. So basically, of course you could perform tasks on, the remaining elements. So if you're in a for loop, for example, and then you're doing some sort of sorting, that could be an example of n log n time. So I think in the previous video we're looking at, there was 2 missing links. There was n log of n, which is faster than constant. It's worse than constant time, but it's faster than linear time, or and also if you have linear time, n log of n ends up being faster than n squared there. So n log of n, so we've sort of seen the intuition behind log of n. If you combine our number guessing game, intuition, with this newfound mathematical underpinning of that, you can see, why logarithm time complexity is faster than linear time. And hopefully this will become even clearer when we see an example in the binary search video. But because it is faster than linear time, if you multiply it with linear time, it's going to be faster than multiplying linear time with itself. So n log of n is going to be faster than n squared. So hopefully that gives you perspective of the time complexities. Which one's the fastest, which ones are the worst. So obviously we're aiming for the fastest time complexity we can possibly solve our algorithm in. So that should be in the back of our mind. But now we actually have a way to rank which algorithms are more efficient than others. So we're able to determine it like that. So recall, we're mostly interested in time complexity, which we've sort of translated to the amount of times we look up a memory slot. And we also want to take into consideration the memory usage, which is the amount of times we assign a variable. So assigning a variable in a loop, it's going to be linear, and it sort of follows the rules of thumbs that we've sort of expressed, the heuristics. But you got to take into consideration each algorithm at hand and what you're actually trying to solve for. So yeah, up until now we've only considered that time complexity has had one result. But for solving Leet Code problems and technical intervals, you only need to give the big O notation, as we discussed in the big O video. So from our sorting example, it's possible that all of our elements are already sorted. So depending on the algorithm used, would result in the time complexity. So we're sort of assuming that you get the answer right, but we're assuming that you're comparing the different approaches to one another, and then in that case we're aiming for the fastest time complexity and or the best space complexity. So yeah, we've seen the sorting example in the previous video where arrays could be completely sorted, or they can be in the complete reverse order. So we sort of discussed why we only care about the worst case scenario, but we will see a couple of those examples. So yeah, we've covered pretty much all the main concepts that we needed to cover. We've introduced data structures and algorithms. We've covered memory. We've covered big O, and we've covered this logarithmic time complexity, which is a special instance of the big O. That's super important. So let's go ahead and just jump into the TypeScript, and we'll start with the array data structure, and we'll begin to solve some algorithms.